Okay, thank you very much. So I'd also like to thank Clara and Bert for organizing the special year and the conference, and for the opportunity to speak on Friday the 13th. Okay. So what I would like to talk about is going to be a little bit different from the subjects we've been hearing so far, but I hope to be able to say more a little later on in the talk about the motivation related to derived categories and stability conditions. So I hope you'll see that, this is maybe not present precisely in what I'll be saying today, but it's the motivation for why we're looking at this. So this is joint work with Lyudmila Katsarkov, Alex Knoll, and Pranav Pandit. We have a paper from last year on arXiv and a paper just recently, maybe a week and a half ago. And so it's from the paper just recently that covers what I'll be speaking about. Okay, so what I'd like to talk about today is just the aspect of harmonic maps to buildings. Okay. So I'd like to start by just giving some basic notations and stuff like that for the buildings. And in fact, we'll be discussing two-dimensional buildings. In fact, buildings for groups such as SL3. So let's see, maybe I should go here. Okay, so these are going to be spaces which are real two-dimensional spaces modeled on a certain affine space. So the affine space is just A, which is R2. But let's give it a more invariant formulation. It's the set of x1, x2. I could probably put 1 here, but it doesn't really matter for what we're doing. Okay, so now the point here is that we have a natural group acting on here, which is the affine Weyl group. What is it? It's S3, the permutations of the coordinates, semi-direct product with A itself, the translations. Okay. So S3 permutes the coordinates. So if we fix a point, this is, you might say this explains why we're doing the case of two-dimensional buildings, is because we can actually picture this affine space as being like the blackboard, okay? So if we fix a point, which we'll think of as an origin, for example, 0, 0, 0, then the stabilizer of the point is just S3, acting as a reflection group. And so we have what you might call the reflection hyperplanes. The reflection lines, and then we can give this space W invariant Euclidean metric. I'll say a little later that's not exactly the distance which is the most useful to think about, but it's good to think to put ourselves in Euclidean geometry. Think of just Euclidean metric, and in that case, the reflection lines are just separated by 60-degree angles. So this is the basic geometrical situation which we're looking at. Okay, kind of simple, but guess you have to draw this kind of thing all the time. I'm not doing too well. So those are supposed to be 60-degree angles, okay? so these hyperplanes are just, for example, x I minus xj equals 0 in this coordinate system. Okay. And that's the reflection hyperplane for the transposition xi, xj. So this determines, you might say, a sort of a geometry on A. So on A, at every point we have these three preferred lines. So that gives us sort of preferred directions inside A. Okay. So now, what kind of structures can we look at? So we can look at let's call them enclosures. An enclosure E inside A is a compact convex subset whose boundary pieces are parallel to these reflection lines. And so we can just draw these. You know, a typical guy will be maybe a hexagon, you might think, or an equilateral triangle, and they're all supposed to be, you know, oriented the same way. Okay. Another interesting one is a parallelogram. What also count as enclosures for the theory are you know, line segments and even a point. Okay. But think more of the two-dimensional pieces. Okay. Now let's see, how are we doing here? Let me, I wanted to just say something here with respect to this picture. So if we have a point, then at this point we have 6 germs of edges starting at that point. And we have 6 germs of sectors. Okay, that'll be important to understand. And the germ of sector is a sort of the germ of what you would call a vial chamber. So a vial chamber is just an infinite piece of pie that with a 60-degree angle, okay, but oriented with respect to these given directions. Okay, so those are enclosures. Now, what are buildings? Buildings are basically things which are built up out of these enclosures by just gluing them together. Okay, gluing them together along edges, or you know, you're allowed to like put an edge in the middle of a piece, but it's always supposed to go in one of these 3 directions. Okay, but let's just call those constructions. So a construction is anything obtained by a space obtained by gluing together enclosures along their standard edges. Okay.
So do you remember the glued edges? Like if I have 2 triangles and I glue them together, I get a parallelogram? And
if you've glued together if you've glued together a parallelogram out of 2 triangles, then you forget that there were 2 triangles. I mean, okay, that's the same as just a parallelogram. Yeah. If you look in our preprint, we also maybe I should say. Pretty much everything I'm going to say here is, you know, conjectural in at some level or not, or another in our preprint, but we were supposed to, you know, write a sort of a sketch of a theory or something, so we wrote sort of a sketch of a theory. So pretty much everything I'll say is somehow or other a sketch of something or other. I hope that most of the things I'll say you'll understand that, you know, it's obviously pretty close to the way things are supposed to work. Among other things, and I don't want to talk about that here because that would take a while and not be very interesting for today's talk. You can imagine a theory where a construction is actually a pre-sheaf on a Grothendieck site of enclosures. You can make a Grothendieck site of enclosures where you say that coverings are, things which cover. But like, this guy is going to be a covering of the parallelogram by two triangles, basically. And the maps are just affine maps given by elements of the Weil group, but only piecewise affine. So, for example, this guy would be allowed to fold like that. So you can, but for today, let's just think of these as just spaces, obtained by gluing these things together. But inside this space, we're supposed to remember these directions at every point. Okay? Every point inside here, inside of one of these guys, is going to have these three directions.
So these spaces locally finite?
No, not necessarily, actually. In general, you want to think of R buildings. So there's a bit of a theory question there. The things we'll see today will be locally finite. And I'll explain a little bit how that works. Okay, so now suppose we have a construction. So suppose F is a construction. And X is a point in F. Then we can define the local spherical construction. The word spherical comes from the term spherical building. What is it? It's a graph, actually. Let me just put this here. It's a graph whose vertices are the edge germs at X. And the edges are the germs of the sector germs. Okay. Now, just one more slight thing to say here is that, in fact, it's a bipartite graph. Which is to say that the vertices are divided into positive and negative vertices. The reason for that is if you look at this diagram, remember we have S3 is acting by reflections here. So the automorphisms that you're allowed to do are just reflecting along one of these lines. But if you think about it, if we label plus, minus, plus, minus, plus, minus, one of these automorphisms is always going to preserve that labeling, right? If we reflect around this line, a minus will go to a minus and a plus will go to a plus. So within this situation, it's a little bit less obvious geometrically, but there's sort of a natural orientation of the edges. Okay. So the local spherical guy is actually a bipartite graph. Okay. Now, and it just says how things are glued together. So, for example, if we take A itself and take its local spherical construction of the origin, it's just a hexagon. Now, so we've been using a number of different references for buildings. Yeah, F is a construction. Okay, so I was going to keep this secret. Okay, but here's an example. Okay, I made some pictures. Okay, this is a construction, right? It's made up of joining together 4 different equilateral triangles. Okay, now what's the local spherical construction at this point going to be? So if we take this guy, let's try to draw it here. Here, there's going to be 4 edges, because there's 4 guys, and 4 vertices and 4 edges. So it's just a square. In a general building, there's like a whole bunch of stuff which come together at a given point. Okay. Yeah, it's the cone at the point, and then we've just sort of reduced the dimension by 1 because If you're, well, so if we take y here, then f index y is just a hexagon. Every single point of this guy, I mean, this may be a slightly different thing for people who are used to working with buildings, but say buildings with edge length, which are integers or something, then you don't use this full group of translations. But here we're using the full group of translations, and all the points are all the same, basically. All the points of A are all the same. And they all have these three directions. Okay.
Okay, so interrupt again, but the gluing in a construction, it should preserve orientation.
It's supposed to preserve orientation. Yeah.
Tetrahedron is not a construction.
A tetrahedron is not allowable. Yeah, that's true. Okay, which is a good point. So that's why we get a bipartite graph here. Okay. Yeah. More technically, it's supposed to be a construction is supposed to be a pre-sheaf on this site, basically. Let's see now. What do I want to say? Because there's still a couple things to say here. While we're here, let me just talk about the Finsler distance. Let's just call that df just in A. The Finsler distance in A is just defined by this. The distance from a point x1, x2, x3 to a point x1 prime, x2 prime, x3 prime is just defined to be the max of x prime I minus xi. But it's not symmetric.
Absolute value or
Remember that the sum of the coordinates is 0, or at least constant. So the differences are in the space where the sum equals 0. So the maximum has to be positive. But that's a good remark that, in fact, if we take df of x prime, and df of x prime x, these determine, since the sum is equal to 0, that means the biggest one and the smallest one determine the middle guy. Okay? So they actually determine the the position of x prime minus x up to S3 action. And for a more general, for a higher dimensional building, you actually want to replace this idea of the Finsler distance. You want to replace it by what you might call a vector distance, which is take the difference, move it into the principal Weil chamber, and then look at that point. Okay. There's kind of for two different points, there's a unique point in the principal Weil chamber, which is the difference of those points. And we sort of think of that as the actual distance. Let's see. So that's the Finsler distance. Okay, now what's a building? That's an enclosure. Oh, so I was saying we've been using several different references, which are all very useful for buildings. The references, maybe I'll put them here. There's a big book by Ken Brown and the guy, I'm sorry I forgot to, Abramanko, yeah, okay. Okay, thank you. There's a paper by Parot. We've actually been using the work of Parot, which brings in buildings as asymptotic cones of symmetric spaces, but which I'm not going to be talking about today. But she also has I think a paper, or part of her paper, which has some discussion of what the axioms are for buildings, and also a useful paper by Bennett. I think there are other also useful references which you can find, some in our references. Sorry. Bennett Schwer, I think, Struve. Yeah. So for example, this paper discusses a number of different equivalences between a number of different systems of axioms for a building. So they're all kind of complicated looking, but we can sort of, once you start looking at all these things, you start to get a pretty good idea, and especially in this two-dimensional case, it's actually not too difficult to figure out what a building is. And one useful thing was in this book, the notion of local spherical building. So let me start with that. So a local spherical building in this context, so for the group SL3, is just a bipartite graph such that any 2 points are contained in a common hexagon, and there's no loops of length strictly less than 6, which is to say 2 or 4. Because of it being bipartite, any loop has to have an even number of lengths. That was the comment about. You can't have a tetrahedron. You can't have a loop of length 3, for example. So this is actually, and at least in this case, it's an extremely simple combinatorial condition, so we feel that we can actually understand what's going on. Now, what about buildings? What about buildings themselves? First, let's say an apartment is just an inclusion from so a building is a construction. Sorry. So building is a construction. An apartment is just an inclusion from A into B, an inclusion of constructions. So this is supposed to, at each point, preserve these structures and so on. It's locally, B is locally an enclosure, and this is locally, should be locally an affine map given by a vowel group element. And here, this is, there's maybe some question about whether you want to look at complete system of apartments or not. So I think we want to look at complete system of apartments. You can also have a theory where you sort of specify some apartments, but not all of them. So, but for here, we'll just say an apartment is just sort of by definition an inclusion like that. Okay, so now what are the axioms? So one sort of convenient system of axioms is that the intersection of two apartments is a Finsler convex subset of each one, which is to say like an enclosure but could be infinite. If you take the same, what I wrote up there, but just take out compact and replace it by closed. If you ask for a closed subset whose boundary edges, convex subset whose boundary edges are, there's finitely many boundary edges and they're parallel to the hyperplanes. But if you think about what I mean by Finsler convex, you see if you have two different points, there's a number of different paths which will realize the Finsler distance between these 2 points. They're sort of all the paths which span the parallelogram. I mean, any path that goes like that is going to calculate this Finsler distance. So the Finsler segment between these 2 points is actually the full parallelogram. And Finsler convex just means if you have two points, then the entire Finsler segment should be contained. Okay. So intersection of two apartments, any two.
So does that mean they can be embedded inside the affine plane? Finsler convex?
Yeah, but these are both apartments, so these are both affine planes. The intersection is in either one of them is one of these guys, And the transformation is a Weyl group transformation. Okay. Any 2 points are contained. Any 2 points are in a common apartment. So if we have x, y, and b, there exists an A. There exists an apartment containing both points, okay? The local spherical constructions are spherical buildings. And this is basically, this is the main condition, in fact. It's a sort of non-positive curvature condition. The fact that we're not allowing loops, where did I put that? Where's my spherical? Did I erase that already?
It's up there, Brian. Right in front of you.
Okay, sorry. Good, thanks. The fact that there's no loops of length 2 or 4, we'll see this geometrically in a minute, this is a non-positive curvature condition. Okay. And then there's just kind of an extension property. For sort of 120-degree angles, which in these texts, for example, is called this property CO or something. That any 2 Weyl sectors starting from a point and opposite are in a common apartment, okay? So let me just draw this last condition. This last condition says that if you have, this is supposed to be a 60-degree sector here. If we have a Weyl sector like that inside the building and another Weyl sector like that, then it's supposed to be in a common apartment. And I think that the we feel, so this again is a little bit conjectural, but we feel that the right way of thinking about that is actually just saying that you can fill in this 120-degree angle here can just be filled in, basically, and the same here. Okay. So, let me just finish this segment of the discussion by defining what's a pre-building. So, what it turns out after we've looked at we'll see this in action here. What turns out to happen is that it doesn't really, for looking at maps from something or other into our building, the notion of building isn't really necessarily the main notion. We can define a pre-building to be something which satisfies sort of many of these properties, but maybe mostly doesn't satisfy the extension property. The idea is just that the extension property is just something which, once you know the rest of the building, if you needed to add in some 120-degree sector, you can just add it in, basically. That's going to be a sort of small object argument going from a pre-building to a building. So a pre-building is a construction say F, such that, well, it doesn't necessarily have a lot of apartments because it's going to be a sort of a smaller thing. But the point is that it's non-positively curved. So, but the Fx the local spherical buildings have no loops of length 2 or 4. And a good property of this is we might also ask it to be Finsler non-concave. Which is that points in Fx or at distance less than or equal to 4. So this is sort of a no Pac-Man condition. You might say, if we have something like this, then we're not actually sure whether we should complete this by adding a single sector here or complete it by adding a 120-degree sector like that, basically. And then this extra sector here sort of starts a new direction in the building. So in a case like that, and similarly, we won't be sure about the distance. If we don't have this condition, then the map from the pre-building to the building might not necessarily preserve distances. Finsler distances. Okay, so that's pre-building. So now let me talk about harmonic maps. So this should really be called locally harmonic maps. It's not going to have an apartment structure. It has an enclosure structure. So remember, a construction is something which is built up out of enclosures. So everybody looks locally like it's locally like a piece of A, basically. But we're not necessarily asking to have a big copy of A inside it. I mean, you can see here. I mean, a typical example is just going to be like, we'll see this. A typical example is going to be everybody except for a 120-degree sector. Then you would just say, okay, I know how to add this 120-degree sector in if I want to, basically. Now, what about harmonic maps? So here, X is the Riemann surface. And we would like to look at maps. So here we're going to look at maps to buildings. Okay, now what's the condition? So the condition let's say continuous. The condition is that there exists a discrete subset so that for any point in the complement of the discrete subset, there exists a neighborhood there exists a neighborhood and an apartment. Such that H maps the neighborhood into the apartment and that this map is by a harmonic function. Okay. So remember that this apartment is just it's just a set of points x1, x2, x3. We can choose two of those for coordinates, for example. So the condition is just that that locally these maps are harmonic maps. Okay. But locally they're maps which map into an apartment, and into that apartment it's harmonic map. I was discussing this last month with Richard Wentworth, who explained to me that that you can have a harmonic map, we can have a locally harmonic map in this sense, which is not actually globally energy minimizing. And that's a slightly subtle point, which I don't think I claim to understand very well. Well, I said it was. That's why I said it was continuous. So, I guess so. Well, you can. Well, yeah, I think we want some kind of finite energy condition or something. I'm not sure if wouldn't continuous sort of imply finite energy? But, no. Okay. Well, okay. Let's add a finite energy condition then. Yeah. Okay, so let's see what I want to say. Yeah, okay, so now if we take on ux, h given by these three functions whose sum is equal to a constant or 0 or something. And let's let just, so we get harmonic differentials dxi. Now, we can recall, this was from Phil's class, in fact, that the real cotangent bundle of x is also the 0, 1, is also the 1, 0 cotangent bundle of x. Okay. The real cotangent bundle of x is also the complex 1, 0 cotangent bundle of x. So the dxi's correspond to differentials of type 1, 0, which we'll call phi I. And the harmonic is going to be that these are holomorphic. Then we can write this in the other direction as being that dxi is the real part of phi I. Okay. If we then think of the phi i's as being full complex cotangent vectors. And now you see that the phi i's are well defined. The coordinates are not really well defined because you could add a constant, but their differentials are well defined. So these phi i's, so phi 1, phi 2, phi 3 is well defined up to permutation. So we can define the spectral curve. The spectral curve is the curve sigma, which is the set of points of the form x, comma, phi I for some I. It's in the cotangent bundle of x. Okay. And let's say that, I guess maybe this is our finite energy condition or something like that. So some condition, some natural condition, is going to say that sigma is actually finite over x. And it's just a three-sheeted ramified cover. And if we assume for a general case, well, let's suppose, for example, that sigma is irreducible. So if sigma is irreducible, we can think of phi without specifying the index, let's say phi dot or something, as a multi-valued one form. Okay. Now we can frame the question which we're looking at. That's a little late. Starting to get a little late for the question, in fact. The question is, given the spectral curve, how can we understand the harmonic map? Now here's the motivation. The motivation is that in the case of SL2, in which case the building is going to be a tree. In this case, the theory is very well known. This is well understood. The the spectral curve corresponds to a quadratic differential. Which defines a foliation with singular in this case, sigma is a 2-to-1 covering. Okay, and for SL2, it's a 2-to-1 covering. There's only plus or minus. There's phi1, phi2, which are plus or minus. Their product is the quadratic differential that determines these two guys. You have this differential real part of phi defines a foliation, and we can let T phi just be the space of leaves. The leaf space of the foliation, and then our map H just kind of automatically factors as a map. There's a map from the space of leaves to whatever tree we were looking at. So, and essentially, I mean, if you think about it a little bit more, essentially B is just going to be obtained by, for generic values for generic differentials, quadratic differentials, any tree that you could map to here is just going to be gotten by mapping to this tree and then adding some extra stuff which is not even hit by the map, basically. So you get a pretty complete description of the possible maps in this case. And now, so here's the sort of derived category motivation, which is that for SL2, the wall crossings for Bridgeland-Smith stability conditions happen when the tree mutates. I was planning to have more of a paragraph on this, but I guess I don't have time. So Bridgeland and Smith have a recent paper where they construct, starting from a Riemann surface plus a quadratic differential, they construct a category and a stability condition. Okay? The category is sort of a derived category of quiver representations. The quiver actually depends on a triangulation, which sort of depends on the Riemann surface and the quadratic differential itself. So as you move around the category, you might sort of have some monodromy or something. But roughly speaking, there's a sort of locally constant family of categories. And then the quadratic differential gives you a stability condition on the categories. And sort of an important role is played by the places where this tree mutates. And these are what are called saddle connections. And these are what Gayoto-Morenitsky call BPS states. So I should probably draw this and emphasize that this is basically figure 32 I saw. Figure 32 in Bridgeland-Smith's paper is essentially the following figure, which is you take, so here we're still in the SL2 case. So we're going to mutate around something, around the following saddle connection. So what is a saddle connection? In this case, it just means a leaf of the foliation that goes between two singular points. Okay? So it's going to look something like that. So our foliation looks like that. There's two branch points of the spectral curve. And they just happen to lie on the same, at a branch point of the spectral curve, there's kind of three singular leaves coming out of it. But in general, the three leaves at one point are not going to hit the three leaves at the other point. But sort of a special point is where one of these leaves here is the same as one of these leaves here. And what happens on both sides of that is this mutation. Okay, so this is a picture of the foliation. I guess for lack of a better blackboard space, let me draw here the picture of the tree, the T-fees. Okay, here are the T-fee. So basically the tree is going to have an edge every time we see this sort of family of leaves, basically. Okay. So here what's happening is that this edge inside the tree is getting smaller and smaller. It becomes a point. And here we have a non-generic tree where there's 4 leaves, there's 4 segments at a point. And then it goes sort of, it changes the direction and goes over here. Okay. So now this is maybe kind of lateral thinking or something like that. But so our idea was to look, and this was actually, I should say, this came up in discussions with Fabian Haydn. So he didn't sort of continue working the rest of the project, but he made some important comments at the start of the project for the motivation. Then he with Katsarkov and Kontsevich also did a newer version of Bridgeland-Smith stability conditions for the SL2 case. But so from discussions, our discussions about this at the start, it became apparent that what we were really looking at here were the leaf space of the foliation considered as a building, basically. So our idea was to look at buildings for SL3. I guess it's kind of an open question how to do this same Bridgeland-Smith type wall crossing for Hitchin bases for higher rank groups, basically. Well, we don't claim to have any progress on that question, but so the idea is to say, okay, let's just consider these buildings as kind of geometric objects associated to the spectral curve. And that's a little bit different from the classical picture where the building sort of shows up by itself. And here we're sort of taking a constructive approach. We're saying, suppose somebody gave us the spectral curve, what could we say about the building? Okay. So our question is, given sigma, how to construct H. So I should probably get my props out here. Okay, so I made some props here. And we've actually basically only done this in this example. This was the example which we did in the first paper in a different way. But also I should, sorry. I should draw this on the board, actually. So this is going to be a picture of the Gayodo-Mornitsky spectral network for the equation so this is a so y is the momentum coordinate direction. This defines a spectral curve which looks like something like, I guess, so we're looking at this in its projection to the x coordinate. There's going to be 2 branch points. But remember, there's 3 differentials at every point. And here's the picture of the spectral network. So I'll use this picture to explain what a spectral network is, okay? So something similar happens at these branch points. At a branch point, there's 2 differentials where when you go around the branch point, the 2 differentials interchange. But the third differential is sort of hanging out there itself also. Maybe the thing to remember also is that our foliation directions are given by real part of phi I minus phi j equals 0. Because remember, our reflection hyperplanes were xi equals xj. Okay. So these lines are going to be foliation lines. They're going to be labeled by an ij, basically. Now, the thing which happens in rank 3 and higher, which didn't happen for quadratic differentials, is we have these things called collisions. This is what we learned from Guyotto-Mornitsky's paper, basically. So when an ij foliation line hits a jk foliation line, they can sort of collide and create an ik spectral network line. Okay, that happens in this picture in 2 places. Now, in this picture, so this picture is what's called this is a classical example of Burke, Nevins, and Rogers, which I guess was the first example, apparently, where some collision kind of phenomena was actually observed in WKB questions.
That's living on the Riemann surface?
Yeah, here the Riemann surface is just the complex line.
That picture, that graph.
Yeah, x equals a c. So this graph is on the Riemann surface. Now, there's an additional structure which happens here, which is called acoustic. An acoustic is a place where the harmonic map has to actually fold the Riemann surface. So remember that we know our assumption on x, which I guess I raised here. Our assumption is that our harmonic map is locally given by just integrating these differential forms phi, taking the real part. So we have a complete local picture of our harmonic map. And along, you have to do the calculation and so on, but along acoustic is a place where these 3 foliations, there's 3 of them. There's 1, 2, 2, 3, and 1, 3. Acoustic is a place where these 3 foliations are tangent. Okay. In general, you have, I guess, what's maybe sometimes called a web of foliations or something like that. At the caustic, the 3 foliations are tangent. They look something like that. And it follows that this has to fold. So I actually did a picture here. So this is the same picture here, just to emphasize, but maybe it's a little bit too small or something. So this is this picture here, okay? But just to emphasize that we're talking about a piece of paper. Okay, talking about a piece of paper. If you're away from a caustic, then the differentials actually provide a coordinate system. And if you pull back sort of the flat Euclidean metric from A, you get a flat metric on the complement of the caustic. That's actually this picture. So this picture is the same as this picture. But where we put a flat metric, and our piece of paper here is given this flat metric, we put a flat metric given by the differentials away from the caustic, and the caustic has to be folded. Okay. Now the question is, how are we going to construct the harmonic map? So the first observation, so now I'm just going to give you guys the construction here with props, okay? We're running out of time. So the first observation is that there's actually neighborhoods. I've drawn these neighborhoods in here. There's neighborhoods, they're kind of big, but you can imagine doing a smaller one if you want. There's neighborhoods of the caustic where you can sort of see that the harmonic map has to actually pinch them together. This example is sort of cheating because actually if you do the same argument that you need to say for this neighborhood, that same argument applied from here to here is actually going to tell you automatically that everybody folds. But we're trying to illustrate a principle, not to. We had already done, using that other argument, we had already treated this example in our previous paper. But here we're trying to get a procedure which in principle shouldn't, again this is a conjecture, but in principle should work for any SL3 spectral network. It should give you the harmonic map. Okay, so these neighborhoods have to fold together. So that means that in this picture they correspond to these segments like that. So the segment here has to be the same as the segment here. So these have to actually fold together under the image of any harmonic map. So we can actually construct that in the following way. So this is supposed to be a picture of the same thing, but here, right, this guy. Oh, sorry, this way. We've kind of extended these parallelograms. We've kind of extended them out here, sort of taken their Finsler convex hull, and here this is only one piece of paper wide, basically up here. Okay. Now, what I want to explain is that the principle of how you go from here to a harmonic map to a building. The point is that we have to impose the non-positive curvature property. So if you think about it, when you do that, let me draw sort of a bigger picture here. If we glue together a piece like that and a piece like that, and then this happens on the other side also of the Riemann surface, we've actually created a point here that has a fourfold loop inside the spherical building. This is a little small, but if you think about it here, there's going to be 4 60-degree sectors here. Okay? So I did a slightly bigger version of that here. Okay? So you're going to get a point which looks like that. Okay? 4 60-degree sectors. This is not allowed in a building. This has positive curvature. The total angle is 240 degrees rather than 360 degrees. Okay? So in the image inside the building, this has to be folded. And kind of the main problem is we don't know whether it's folded like that or like that. Okay? There's 2 possibilities. And I think this is kind of a guess, but there might be some sort of analog with birational geometry in which this sort of becomes analog to like a flip or a flop or something like that. I'm not sure about that. Flop, okay. Well, anyway, so what we know a little bit more here actually. We know that points, let's see, where are we? Points around here, for example, these are going to be points along one of these segments, okay? We actually know from our hypothesis that these have to go by a flat map into the building, okay? This was our hypothesis of having a harmonic map. So the picture is actually more like this one, which is the same one, but I don't know if you can see, but this is just a single sheet of paper, okay? So we know that our hypothesis is telling us that neighborhoods here have to actually not be folded. And that's going to tell us which direction to fold, basically. Now, the conjecture is that we can sort of follow this information along as we proceed and always keep enough information to decide which direction needs to be folded every time we come to one of these points of order 4. That's a conjecture, and it's certainly not true. I mean, maybe not, certainly not true, but so our conjectured statement, in fact, is that if there are no BPS states, put up our conjectured statement. Then basically, then the universal pre-building exists. But then our harmonic map has to factor through a universal guy, which is obtained by the procedure which I'm about to illustrate, starting from our Riemann surface. Okay, so what's the procedure? The procedure is just we take our guy, which we started to pinch together some pieces. Now we just notice that these parallelograms have to be pinched together, and now we know which direction they need to be pinched together. So we can just pinch them together. And we can also cut out the previous guys. I'm not going to do that here, but we could just remove these guys first and then pinch these guys together, and you get this picture. But here we sort of removed these guys, which were already just a single piece. Okay, we just cut them and throw them away, and then we pinch together the next pieces, so we get some more single sheets of paper here. Then we have, in this case, we just have one more 4-fold point which needs to be contracted. So then we can again cut these guys off and pinch things together, and we eventually get down to this picture. Okay, this is a nice picture of a negatively curved point. Okay. This is a point with 8 60-degree sectors, so there's a total angle of 480 degrees. Okay. So we get down to this guy. Then if you think about it, if we wanted to have a map from our original Riemann surface into here, we actually just chopped, we threw away a few things. So if we just put them back, but just in a single sheet, then if we sort of glue this piece in here, then that should be that's the pre-building. And I saw a nice talk here in the mathematical conversations thing by Doron Puder, who was explaining the process of Stalling's graphs and Stalling core graphs. When I saw this talk, I said, hey, that looks exactly like the same thing we're doing, which is to say there's some folding, if you guys went to that talk, there's some folding process where we have to fold these guys together. Okay? That's going to be like this process of collapsing edges, which Duran explained. And then there's this trimming away process. Okay? And we get down to something which I would call sort of the core of the situation. Okay? So now the hope of this, this is as far as we've gotten, basically. You can see more details in the preprint. The hope is that by studying maybe these core pieces or the entire pre-building and trying to understand how they mutate when we change the quadratic differential, the hope is that that might give some geometrical structure which might correspond in some way to this Ridgeland-Smith stability conditions and Kontsevich-Soibelman wall crossing for these objects. Okay, so I'll stop here.